last lecture by Professor Madsen.
Yeah. I look very much forward to this, that it's the last lecture. So just to summarize what I have told you, I'm trying to give you examples of theoretical tools needed to investigate strong field physics and atom tunneling, TDSC, strong field approximation, and so on. We had some discussion about electronuclear correlation. What we haven't discussed, in fact, in any talk, more or less, well, in some sense, but not in the non-determinant sense, we have not discussed very much the effects of electron-electron correlation. And this is the topic of this talk, and it will also be, in fact, the topic of the next talk. Right? Yeah. So today you will hear something about electron correlation. And this is about the fact that electrons interact, but this is actually the reason why there's still people doing AMO physics. Because if electrons were not interacting, it would be completely trivial. The wave functions would be product wave functions of orbitals. And a single configuration of orbitals would describe everything. So the difficulty is to describe small electrons. This is a problem that quantum chemistry has treated for many, many years. But they have never looked at time-dependent electrons. And in particular, they have never looked at the problem when these electrons fly apart. And this is a challenge for them because this means that the dimensionality of the problem is just huge compared to any standard quantum chemical problem. And that's why it's still a challenge just to solve two electrons in the presence of a strong field. So, motivation. Let's just go through this once more. So, new light sources could focus on time-dependent unperturbed dynamics. This is a fundamental problem. I actually think about this as one of the unsolved problems in theory with respect to the non-relativistic Schrödinger equation. So when you drive a quantum system strongly out of equilibrium, it's extremely difficult to describe. This is why this is a fundamental problem. Then we have different characteristics with these new light sources. Valence electrons, the least bound ones, they ionize most readily by tunneling-like processes. The wavelength is long, as we have discussed. But if you now have, for example, higher frequencies, the wavelength is so small of the light that it kind of penetrates the atom and hits the inner orbitals. So you can have initial induced processes also. So this is a wide range of different processes, and from a theoretical perspective, it's extremely challenging to make one method that works for this type of physics and also for this type of physics. But this, nevertheless, could be some kind of ambitious goal. Moreover, as you know by now, observables are most often associated with processes like ionization, breakup, high-order harmonic generation, transient absorption. All of these processes, well, perhaps not transient absorption spectroscopy necessarily, but all of the other ones definitely involve continua. So electrons that move away have positive energy or nuclei that break up. And that's because this is how nature reacts, but it's also important for us to maybe think about that this is interesting from the point of time-resolved studies. Because if we have a very, very short pulse and we ionize the system, we get response readily read out by measuring that electron following that ionization, right? So if there's a very direct link between, for example, ionization at different probe delays and following some dynamics of the system. So for interpretation of time-dependent dynamics in a system, this is also good. You need a fast readout to follow the dynamics. And ionization and such breakup processes are examples of this. At this point, much insight has been obtained by single active electron approximations. So what does this mean? It means that we simply just take the valence and then let it move in some effective potential. But of course, a range of processes involve correlation. And one example that we saw yesterday, I think, was this example of, maybe, I mean, things are now getting complicated to remember. But at some point we saw the example of ionization of helium, right? Single and double ionization of helium. And there was this term non-sequential double ionization. There was this knee enhancement in the double ionization helium. And this type of stuff cannot be explained without electron correlation. So that's just one example. It's kind of an old example, but it's an example. What else? Well, as I said, direct solution of the time-dependent Schrödinger equation is limited to very few particles. For example, hydrogen, helium, H2 plus, maybe H2. And so we have to do something else here. And this is simply just because of the dimensionality of the problem. Because if you want, for example, if you want to describe ionization, you need a large box, maybe 1,000 atomic units. You need maybe grid points at 0.1 atomic units, so then you can calculate how many grid points you have in one direction. If you now have 3 directions for each particle, and you have n particles, you see that this will quickly be impossible to have it in a computer. So therefore, there are many people are beginning now to develop other methods here, and all this stuff here is found in the literature. So of course, time-dependent Hasse-Fock, maybe you have some idea. I'll tell you briefly about Hasse-Fock. Time-dependent CI singles is something you also see in the literature. I'll tell you about what this is. Multi-configuration of time-dependent Hasse-Fock. Time-dependent coupled cluster, orbital adapted time-dependent coupled cluster, time-dependent R matrix, complete active space, self-consistent field methods. All this stuff is I have to say my background is not in this many-electron theory. So I started learning this like 5 years ago, 4 or 5 years ago. So you have to pay kind of a high price to enter this business because you need to know what does all this stuff mean here. But it's possible to learn, and I'll give you some good references. At this point, these two methods have found most applications. I'll come back to this one in particular and tell you what it means. But before we do that, I think maybe just remember Hasse-Fock. And I remember that we should remember Hasse-Fock just a minute ago. So therefore I found this picture on the internet and inserted it in the talk. It's very difficult to read. But I think we can still see that here I have an orbital phi I, eigenenergy epsilon I, and here I have one body Hamiltonian with the kinetic energy and interaction with the nucleus. And here I have another orbital phi j, which is occupied, and I sum over all these occupied orbitals, and then I make an integral. So this is the mean field of all the other electrons on this one. And then we have to remember that electrons are fermions. So there is another term where instead of j here I have I. So this is the exchange term. So this is mean field Hasse-Fock. The electron moves in the mean field of all the other ones. And this is extremely easy to solve because it's a one-orbital equation. And also the time-dependent version of this is very easy to solve. But as I said in the motivation, for many purposes this is not enough. We have to go beyond the mean field. And the approach that one could take, and this is what we have done, is to say, well, it's probably naive not to try to learn from quantum chemistry because they have learned a lot over many years. So what we did, and what I would recommend if you're interested in many electron problem, is to start out by studying some quantum chemistry methods and some quantum theory, quantum chemistry theory books. And I put here in the talk, in the lecture, I put 2 good books. This is probably the easier one, and this is a more advanced one. But they will, if you study those 2, you will have an extremely good understanding of Hasse-Fock, of annihilation and creation operators, field operators, and all this kind of stuff. So this is the starting point. This is what we do first. So now I assume we have done this somehow. And then the challenge is to identify methods used in quantum chemistry and try to extend them into the time domain. And so far we have, in my group, we have mainly looked at 2 different ways to do this. So this will be the topic for the rest of the talk. Do you have any questions at this point? basically. Then I will mention the approaches, and I'll try to explain you some of the advantages and the difficulties here. So the two approaches we have identified, of course, also have kind of long names according to the tradition. And when you work in this field, these names actually give you some information. So the first one is time-dependent restricted active space self-consistent field method. So yeah, so this self-consistent field has a Fock theory. If you saw the formula assumes that you have some kind of iterative procedure. You have to get some orbitals, evaluate the integrals, and then iterate. This step is what is described by self-consistent field. When you have a theory where the orbitals are updated, it's called a self-consistent field theory. And so this I will explain, and explicitly here in the ansatz for the many-electron wave function, you see that this here is a Slater determinant. This is my shorthand notation for Slater determinant, and this index I here is a string of indices telling me what orbitals are occupied in that particular Slater determinant. So maybe it's good to give a small example on the blackboard. I'm sorry.
No.
So, for example, when we talk about Slater determinants, we can think in this picture here. This is maybe the ground state configuration of the volume. I have 4 electrons in 2 spatial orbitals, but that's allowed because they can point up and down in space, right? So this would then be one of those I's here, right? But then maybe another one would be this one here, where maybe I have taken one up, right? So here I have excited one of the occupied ones to something which is maybe unoccupied, which would be a virtual orbital. So this would be another Slater determinant. Okay. And yeah.
Do these methods actually take into account the spin dependence or not?
Yeah, they take into account the spin dependence. So this here is with time-dependent orbitals, and then we have another one which is called time-dependent general active space configuration interaction method. It's more or less the same, except that the orbitals are not updated in time. This one here is much more difficult theoretically than this one down here, so I'll start by discussing this. So now, and I'll also explain why we need to have some active space. It's because if you just allow all, just briefly, what this means is that if I allow this I here to run all possible kind of excitation schemes, the number of determinants explodes exponentially, in fact. And this here is a clever way, based on physical understanding of the process, to say, probably for this particular problem, it's most important to include these kind of configurations. Right? So for example, if I have an 800 nanometer field, it's probably not important to include the 1s in the atom very accurately if I have, say, 6 electrons. Right? So then the 1s is probably not very active, and this is taken care of. Is that concept clear? So these are the two. So let's start with this, what I call the simpler theory. And this one then consists of apparently 3 parts. Here you can see one part is about theory, and one part is about some examples, and one part is about the conclusion. So let's look at the theory part. So the method is called time-dependent general active space configuration interaction. Let's first consider time-dependent configuration interaction theory. This is basically this ansatz again for the many-electron wave function, a linear combination of different Slater determinants with appropriate coefficients here. So now I stuff this guy here into the time-dependent Schrödinger equation, and then I make a projection on one of these Slater determinants. For example, Slater determinant phi I, and then I get this set of coupled equations here. This step is completely standard. You're used to this step, maybe not with Slater determinants, but then maybe just some Cn, phi n kind of things. And then you know that you get such kind of coupled equations here. And now the one other important point here is that if you plan to embark on this multi-electron stuff, I would highly advocate that you use the language of annihilation and creation operators. Because if you do that, you don't have to worry about explicitly anti-symmetrization. All that is taken care of. And this means that this Hij here is written down in terms of these annihilation and creation operators. And here you then have the expectation value of the one-body Hamiltonian kinetic energy, potential energy, between orbital I and J. And here you have the Coulomb interaction between orbitals I, J, and KL. Right? So this is two-body operator. And another thing which, if you come from what kind of normal wave function background, I also want to stress that this stuff here is, I mean, it's not that here you don't represent the wave function for this, because this guy here can be obtained from the vacuum state with no electrons acting with suitable creation operators. So you have like vacuum as a bunch of creation operators, and then you have these guys here, and then the same here, vacuum, and then annihilation operators. And then it's just a matter of applying anti-commutation rules here for these creation and annihilation operators to figure out whether this matrix element can give something or not. Right? So this is a big difference, and it's also so we're very used to, and also in many of the talks you've seen kind of wave packets moving around. To do that in this type of formalism, one has to do a slightly different approach. Anyway, this is now the equation we have to solve. And if I don't put any restriction on this here, I have this basis size.
Excuse me.
Yeah.
Is W also time dependent? WIJKL?
No. No. No, because this is the electron-electron interaction. So 1 over R1 minus R2. This one is time dependent because the interaction with the field, for example, in length scales F dot R, where F is time dependent. So this is included in the one-body operator. Yeah. And so now we can ask, how big is the basis size? Let's assume that I have NB basis functions. And then I have maybe n electrons, but let's consider this what we call restricted types of Fock, so I have an even number of electrons, or restricted ansatz where I have an even number of electrons. So each orbital describes both spin up and spin down. Right? This is what I somehow also assume here, one orbital here in the spatial part, and then one spin up and one spin down. So this means that I only have to kind of put any half electrons into my NB basis states. This factor of 2 is not so important. This may be better just to say you have NB basis states, you have to distribute n electrons in those NB basis states. This gives this binomial coefficient 12.
That's what I asked before.
Yeah.
The orbitals are spin independent.
Yeah. Okay. Yeah. Yes. Good. Now. Yeah.
How do you add the ionization process?
I mean, this is the exact Hamiltonian.
Ionization.
Yeah, it's not. Yes, because when you look.
You can lose the electron.
Yes, exactly.
You can have even atoms of creation ionization.
No, I mean the electron is still there, it's just far away, right? So yeah.
So those phi I to the.
This is okay. Now yeah. In fact, the question is very good. At first, I thought it was a stupid question, but now it's a good question. So it's like this phi I here. The question is what does this one include? And in fact, it somehow includes something you could call kind of bound state orbitals. Here, so here I have a bunch of bound state orbitals, and then out here I have maybe one electron somewhere in the continuum. And one way to think about it in this quantized formalism is to say that, well, maybe my one electron in the continuum in this particular basis function is at this position. And then some other basis function, it would be at this position. This is like in a number state representation. This will become clearer when we see. Yeah?
Is the basis set changing in time, or?
No, in this one the basis set is fixed. So this is the easier one. Okay, so anyway, this one here in this kind of research field, this problem here with this exponential increase in the number of basis size is referred to as the curse of dimensionality. And therefore, what the task is to decrease the basis size. And to do that, we invoke some schemes and concepts from quantum chemistry. And here we go. And this now I want to explain this. It's very physically and easy to understand in a way. So I thought this would be a good chance to show you. Let's try to construct a generalized active space wave function. What we then do, so let's assume this is the system. I have 1, 2, 3, 4, 5, 6, 8 electrons. What I then do is that I partition the single particle basis into some parts, in this case NR parts, where NR is 1, 2, 3, 4, I have 4 spaces, okay? And then what I do is that I then impose restrictions on the particle numbers in the different parts. For example, the core, we can call this one here. If I say I always have to have 2 particles in this space, then these guys are not allowed to move. And this we refer to as the core is frozen. And if, for example, single excitation out of P1 is allowed, well, then if I allow single excitation out of this space, for example, going up there to some of the instruments, then I can have either 2 or 1 in this space. This is stated here. And then once we have specified this, we construct the configurations of the subspace. Here's an example. And so now in this case, I have these subspaces, and I want to give you this example where I say, you can think about this as if this is maybe some space appropriate for describing strong field ionization. Because I say I want to have always 2 electrons in the P1 space, I always want to have 4 electrons in the P2 space. So basically this means that this is frozen and this is frozen. And then in the P3 space, apparently I say, okay, in P3 I can have either 2, but I could also have 1. If I have 2, I have no electrons in P4, but if I have 1, I have 1 electron in P4. This is the idea. And here I wrote out explicitly in a number state representation, so you know the number state representation from when you quantize the electromagnetic field, right? Somehow, yeah. So 1, 1, that's these 2, 1, 1, 1, 1, that's these 4. And 1, 1, up, down, 0, 0, 0, 0. That's 1, and then you get, this is what you get. And if you didn't have those restrictions here, if you just work with these states, 1, 2, 3, 4, 5, 6 states, instead of having these restrictions, and you allow all different kinds of excitations, you can do that as an exercise if you have the energy to do it later. You'll see you get, even for this very simple exam, many more configurations. So this is the general idea. And here, this view graph here illustrates how general this is. For example, if I have such a partition here, I could have, I say I want to have 4 electrons here in this space and no electrons anywhere else. Then this would just be the ground state as Fock configuration. I could also say I want to have 1 of these electrons and allow it to move around. Then this is, then this would be a single active electron approximation. This particular version is in fact a little bit. I personally like this because, as you will see, you don't have to feed any potential. It comes out automatically. This one here is interesting. This has been applied a lot recently. This is. In this particular case, we have a fixed core, but the important part is that we can allow only single excitation. You see, I want to have either 2 or 1, so this is with single excitation out of this state. This is therefore referred to as CI, configuration interaction, with singles. So when you in this literature read singles, doubles, triples, it means how many excitations can I have up here, right? So this singles is also included, and of course I could also freeze the core, and then I could have a P2 space where I have more states, and in this way add more correlation. So this is the idea. So okay, now a few technical notes here, because I thought it would also be. I mean, I want you to know how we do this in practice. I don't want you to I don't expect you to understand this, but I want to give you the words. We need to represent those wave functions or orbitals in some manner, right? And what people tend to do a lot now is to use something which is called find element discrete variable representation basic function. And here is some picture of these, and it's a kind of localized basis, and it has some very nice properties, and you have some formulas here. Never mind the details. I put here for your convenience the original paper. Well, now I'm not sure whether it's original, but this is a good paper to read if you want to know about find element discrete variable representation. So, a nice thing about this, and this is why we want to use it, is that the potential, which is local in coordinate space, is diagonal in this basis. This is a huge advantage. This means that if you think about a matrix representation of operators, it's of course much better to have a matrix which is diagonal, which is the case here, than a matrix that's completely filled up. Also, the kinetic energy part has some nice properties. I don't have a picture here, but what this equation tells you is that the kinetic operator is kind of block diagonal. So within one element, it's kind of full, but then there are different elements. That's why it's called find element. So you have a block diagonal structure in the kinetic energy part. And also the electron-electron interaction is diagonal. This is now a key point, because this means that to store the electron-electron matrix elements, because it's diagonal, this find element DBR basis, you only need NB squared instead of NB to the power 4 matrix element. So this is a big advantage. So it seems that this find element PBR basis is very good. Here is a picture of the basis, because it provides very efficient storage of the two electron intervals. But there is also a drawback. It's very difficult to say, should I include this basis function? Is this basis function important to include? Probably it is. Maybe this one is also important to include. But maybe also someone out here, it's very difficult for me to see which ones to include and which ones not to include. And therefore this leads to, basically, you have to include all of them if you just use these FEDBR basis functions. The solution to this could be maybe to include configurations based on Hartree-Fock orbitals here to describe the bound state parts. So this here is the ground state Hartree-Fock orbital, and this is the first excited Hartree-Fock orbital. These are probably important to describe the structure initially. Right, so now we can come back to your question. So we have this system. We need to describe the bound state part. It's of course here. So it's these functions here. But then also we need to describe this electron that goes up here. And for this we can use this basis, this FEDBR basis. So that's the idea. The drawback with the Hartree-Fock is that the virtual orbitals means the orbitals that are not occupied. They're very delocalized. So this is shown here, but this one here and this one here, they're very delocalized. They're not very good at describing structure close to the origin here. And the solution to this is to use something called pseudo-orbitals instead of virtual Hartree-Fock orbitals. And what is pseudo-orbitals? It's extremely simple. It's just orbitals that you make where you throw away the mean field. So now you just have, so the pseudo-orbitals are constructed by just taking the kinetic energy and the Coulomb attraction. So this means that what we do here to describe the bound state part is that we have some Hartree-Fock orbitals and some pseudo-orbitals. When you start reading about this type of stuff, you will see long discussions also about